Hi, this is Chapter 9 on differential equations. So first off, the important thing in this chapter is it's going to be an experiential chapter, and we're not going to do much theory, but we're also going to do an application project which is kind of fun, and I will send you a link for a Excel spreadsheet for this project. So first off, differential equations are when things are being described in terms of a rate. So let's just look at the fact that approximately all people in the U.S. have 2.1 children over their lifetime. Now, what does that mean? Well, first off, men can't have babies. So you can either think of it in terms of pairs, or each woman has 2.1 children, but only half the world is female. But let's just take a look at what that means over, let's say, a 30-year lifespan. Let's suppose we have 15 couples, all, let's say, married at age 20, and none have kids yet. Well, now, 30 years later, they're age 50. Well, that means 2.1 children per couple. So we have 33, let's say 30 plus 32 kids. So now we are at 47 people. Now, we've had no deaths or anything else happen, but now let's take a look at it without them being couples and simply say, let's say we have 300 people. Now, if we assume they're about 50-50, that says 150 of them are women, and they average 2.1 children per woman. So we'll take 150 times 2.1. $315 kids. And we'll get 615. And again, let's assume this is child-rearing people. This is a period over 30 years. So what's happening is there's a period of time in which what's happening is the following, that the change in the population over a period of time is approximately some constant multiple times the existing population. So the constant multiple that was multiplied times the existing population here was a multiple that allowed 32 people to be born from 15 couples, or 315 people to be born from 300 people. This number is a consequence of 2.1 over some given time period. So let's just write down that differential equation. And observe that the following differential equation is satisfied by this equation, this function. So the derivative of p is a e to the kt times k, which is k times p. So this function satisfies that differential equation. So let's see if we can figure out the function that produces 2.1 children per couple when we start with, let's say, 300 people. So at time equals 0, I want to have 300 people. And 30 years later, that same group, I want no one to die. And we figured out that we want 615. I claim there's a differential equation that goes through that by doing the following. P of 0 is a e to the k times 0, which is a, which I set equal to 300. So now P of t is 300 e to the kt. And now I'm going to put in 30 years. And claim 615. And so now e to the 30k equals 615 over 300, which is e to the 30k equals, that was the 2.1. And then we'll take the ln of both sides. 30k is ln of 2.1. K is ln of 2.1 over 30. And now, this is actually an annual reproductive rate. So we've created a model which describes how the society of North American people have children. Now, the overall reproductive rate is actually what's being calculated when we say 2.1, because some people die in their youth and some people don't have children, but it averages out. This is the exponential growth model. Now, I'm pretty certain that we'll all agree the exponential growth model will go to infinity, and we don't have that much space on Earth. So let's come up with a slightly different model. So let's come up with a model that says that the growth rate for small populations is going to be like k times p. So it's going to grow exponentially. But as you grow and get larger and larger, you're going to use up resources, and there's going to be fewer places to live, and it's more difficult to survive. Just think of trying to put more and more and more rabbits in a pasture, and reaches a certain point in which they can't live because they've eaten up all of the grass. So, well, let's also say that we want dp dt to be very small when p is large. So, how can I accomplish that? Well, I'm going to try it with the following equation. If you look at page 612, I'm going to set dp dt equal to kp times 1 minus p over some number m. M is frequently referred to as the carrying capacity. So, first off, let's suppose the population has finally reached m. Well, 1 minus 1 is 0, so there's no growth. So it's flattened off. And let's assume the population is very small compared to m. Then p over m is very close to 0, 1 minus p over m is very close to 1, and therefore the growth rate is proportional to the population when p is very small. Well, a picture of that looks like this. At t equals 0, we have a very small population, and it grows rapidly because this is basically gone. But after a long enough period of time, we reach a value close to m, we're going to flatten out. So it appears that this is statistically or numerically what this equation looks like. Now, how would we solve this equation? Well, almost all differential equations are solved that are easy in a method called separability. This is on page 613. So if I write down dp dt is equal to kp times 1 minus p, one way is to get the p's, which are the variables, on the left side, and t's, which are the other variable, on the other side, and the k and the m, they're just constant. They're part of the problem. So I'll write dp over p times 1 minus p over m is equal to k dt. And that's treating the dp dt as the Leibniz fractional equation. But then I'm going to integrate both sides, and this becomes kt. And this over here, under partial fraction decomposition, is going to become something over p and something over 1 minus p minus m dt. Now, what does that mean? It means that we actually have two logarithms over here, and we get a log p plus a b log 1 minus p over m, but we've got to have a multiplier in there, and let's see, the derivative is 1 over p minus m times minus 1 over m, so we'd have, I believe, a minus m here. And this will be equal to kt. And now when it's all done, there's a plus a constant. Let's not worry about this process here. What happens next is we actually try to solve for p. And what's interesting is that we can, using some algebra and some logarithms, and we get p equals m over 1 plus a e to the minus kt. Now let's take a look at this function. First off, we're going to put in t equals 0, and we're going to observe that e to the 0 is 1, so we're going to get a value of m over 1 plus a. So that's the initial population. Now, we also know that the derivative of this when the population is very small, it's going to grow exponentially. So why does this flatten out? Well, let's take the limit as t goes to infinity of p of t. And we have m divided 1 plus a e to the minus kt. And now as t goes to infinity, as long as k is a positive number, then minus kt, this goes to 0, and we're going to get m out of here. So what happens is stabilizing. And so this function does what we thought it was going to do. Now, this function actually arose in a way where we chose a model. It's called the logistic equation, and it allows something to grow quickly in the beginning and slower at the end, much like the number of people that are getting infection with the virus. M being the carrying capacity would be, let's say, the number of people that could be infected, and P could be the population of the infected people. So this could also be a model for disease spread. And it simply says that through time, if we will look at not the total of people getting infected, but the new cases would rise rapidly in the beginning, but then there'd be fewer and fewer new cases, and it was going to drop down. So this implies a new case picture that looks like that. All right. Differential equations actually take a form much like this, where we say I have a derivative, maybe a second derivative, plus, let's say, the sine of x times the derivative equals 3 times the function. That's a differential equation. The variable might be x or t, it's suppressed. We're interested in finding out whether something solves it. And that's very hard. There's an entire course about that. So the general thing that we're going to do with differential equations is we're going to give you an equation. We're going to say plug in a value, a function, and see if it works. So let's try, in this case, y equals the cosine of 3x. Let's see if that solved this differential equation. Well, first we take y prime, which will be minus 3 sine of 3x, and then we'll do y double prime equals minus 9 cosine of 3x, and I'll stick it in there. I'll get minus 9 cosine of 3x plus the sine of x times minus 3 sine of 3x, and then you'd ask, well, is that equal to 3 cosine of 3x? Now, I don't know if you believe that or not. I don't think it looks very likely, because if you believed in that equality, you'd put this to the other side, divide by a minus 3, you'd be saying that the sine of x times the sine of 3x would be equal to 12 divided by 3, negative 4 cosine of 3x. I don't know if that's a well-known trig identity. I don't think it is. So it appears to be pretty clear that this doesn't solve that equation. So finding the solutions, what we did first was called separability. Separability is a useful technique, but it only happens on a very few cases. Now, the next thing I'm going to do is I'm going to talk about that differential equations can be kind of complicated in the sense that they describe something that's happening. What does it mean that something is happening? Well, let's think of wolves or foxes and rabbits. Now, wouldn't it make sense if that the wolves are high in number, that this is going to cause the rabbits to decrease because they're going to eat so many of them? In fact, they're going to eat so many, they're going to out-eat the number of rabbits being born. Now, as the wolves eat up the rabbits, if the wolves are high and the rabbits are low, it seems to me that this says the rabbits can hide, that the wolves are going to start starving, and the consequence is the wolf population will probably drop dramatically, and the remaining rabbits hopefully can survive. Let's write down an equation that might describe this. Now the equation that I'm going to write down is a well-known equation for predator-prey equations. This is from page 628. And its name is the Lotka-Volterra equation. And it looks something like this. Let's say that the rabbits are growing in the following way. First off, it's a multiple of the rabbit population. So they're going to grow exponentially. However, we're going to suppress them by some multiple of the product of the number of rabbits and wolves. So as this number gets large, if there's a large number of wolves or if there's a large number of rabbits, the product is large, this will suppress the rabbit reproductive rate. In fact, this can overwhelm this and the rabbits can start decreasing. Then we're going to do the same thing with the wolves. We're going to say that the wolves gain through time. First off, if there are too many wolves, we're going to claim that their population is going to drop off. Why? Because they've overproduced. But the wolves are going to grow at some multiple of the product of the number of rabbits and wolves. So if there's lots of prey and lots of wolves, they will grow. But too many wolves, they'll decrease. Now this is called a coupled differential equation. And it's very, very, very hard to solve these things. So what we often do is the following. We create what's called a phase diagram. And what we're going to do is I'm going to put the rabbits here and the wolves over here. I want you to imagine that this equation, we're going to evaluate it at some specific rabbit number and specific wolf number. So we'll put that in here, and this will say whether the rabbits and wolves are increasing in time. Well, this is a W and R graph. I don't have time in here, so I do want you to notice that if I do dW dt divided by dr dt, that it would be reasonable to call that dW dr. And in fact, this is a consequence of the chain rule. If you put the dr dt on this side, dW dr times dr dt is dW dt. So I can actually take from this equation, I can evaluate this equation, get a dr dt, a dW dt, take the ratio, and I can plot in here a point, R0, W0, and then I can plot the trend of how the W is changing with respect to R. So if I drew this derivative, that says the rabbits, as they increase at this moment in time, the wolves are decreasing. Now there could be another point here in R1, W1, and at this point, if I evaluate it and I discover that dW dt divided by dr dt is positive, then the wolves might be increasing. This doing of evaluating the differential equations at different points and plotting the trend relating the two is a very useful technique to determine what a solution might look like. So I'm going to draw, I'll come back to that one, I'm going to draw, this is called a direction field for the logistic equation dp dt equals kp 1 minus p over m. It turns out that when you put different values of time and p into here, you're going to get little directions that look like this, and they seem to get steeper and steeper and steeper, but then they seem to get flatter and flatter and flatter and flatter, and then they look something like this. This is what the evaluation of this equation looks like for a fixed m, a fixed k, and different values of p and t. And now when we plug them in, if you actually have a point, let's say this is my known point, then this predicts how your function is going to behave in time. And it's an initial point that decides which function you're using. They're all going to look alike because of this direction field. But you take a specific point to get a specific answer. So now I'm going to return to this one. It turns out a very common predator-prey model looks like this. Lots of direction lines in this thing. I'm going to put in lots of them in a different way. It turns out if we take lots of different points and we evaluate this original strange coupled differential equation at various values of r and w and then take their quotient, we started getting values like this. What this means is that if you have a specific rabbit-wolf population, let's suppose it's here, then we can predict the next moment, and then we can predict the next moment, and then we can predict the next moment, and we can predict, and this can start predicting how the rabbit and wolf population dynamically changes in time. Now, it's pretty clear that something like this phase diagram between W and R, is not necessarily going to be a function at all. Could be an orbit, etc. So what people frequently do with a solution like that is they'll draw wolves as a function of time, and on the same graph they might draw rabbits as a function of time. And so here's a pretty common one. I'm looking at the graph on page 631. Here's my rabbit population. Why is it being suppressed? Why is it being knocked down? Because all of a sudden the wolves get a head up on the rabbits, causes them to start dying off. But that causes the wolves to die off, and then we get this cyclic behavior. Oops, I think I got it backwards. Cyclic behavior. Yes. As the wolves start growing, they start outcompeting the rabbit's birth rate, and the rabbits drop off. And now once enough rabbits have died, then the wolves die off. Then the rabbits recover. Then the wolves recover. And so the rabbits lead the wolves. When they grow well, then the wolves recover, predate the rabbits. Then they drop off. Then the wolves, and this oscillates. This actually frequently produces a graph that looks something like this when we put wolves versus the rabbits. And it oscillates through time. We're heading towards creating parametric equations, but this is what we're really interested in doing. We're trying to understand how rates are related to one another in complicated settings. Now, our project that we're going to do on Excel, or OpenOffice Libre, will be an application of the Lotka-Volterra one, so we can actually see an orbit happen. Now, these phase orbits can do something interesting. For example, they could do something like this, which says the rabbits grew and then the wolves grew, but then the wolves all died off. And now it's just no wolves and the rabbits are there. Or something like this could happen. They could start spiraling into a stable point to a specific number of rabbits and a specific number of wolves. Or it could be chaotic. And if you've ever seen a spirograph, here might be an actual orbit of rabbits and wolves. And why that happens is perhaps very, very subtle. All right.